Greetings, welcome to DAU's AI video learning series. Today we're going to do a deeper dive into how AI learns to see. We were going to do RNNs and we may get to that in a part 3, but we didn't get near as much done in the last CNN video, convolutional neural net video, as I'd like to. So we'll do a deeper dive into CNNs and see how that goes. Okay, so last time we talked about CNNs that were used for the labeling of this, and recurring neural networks would be maybe used for the tracking and other things we'll get into later. But right now we're just going to talk about the basics again, CNNs, but this time just get a little deeper into that. And last time we talked about first, for any computer or AI system to see, the data has to be converted to numerical values, and they see basically through numerical data, and that's what AI systems do. They learn from patterns in AI data, so that's really what we're doing here. Okay, and we talked about in the early days when we first tried to use neural nets to detect imagery and video. We tried to wire them up directly to pixels, and here we showed a 256 by 256 pixel image, and we tried to wire that directly to a neuron layer of 128 by 128 neurons. And we talked about red, green, and blue to make that 3 times 256 by 256. I mean, 3 billion connections to those 128 by 128 neurons, and that just wouldn't have been tenable with all those parameters. And that was just the first layer. We'd had to have multiple layers of that to make that work, and it just didn't work, and it wasn't practical. So engineers then looked toward nature and the human eye and how the human eye works. And the human eye just has a very small bit on the back of your retina about the size of a pencil eraser that sees detailed vision. And that gets stitched together by your brain, and to you it looks like the whole picture is detailed. So engineers turned to that feature, called it convolution, and we came up with using neurons in a slightly different way, more like the eye uses it in the optical part of the eye. And we use a neuron as a filter, convolutional filter. And if you take the neuron and you wire it to a smaller image, here we see a 3 by 3 kernel, and then you take the output of that, you can make another image of it, we call it a feature map. And as you move that over the bigger image, it's called convolving it, and you convolve it over the bigger image while you build a smaller image or another image called a feature map. And the filter, depending on the way it's set, will filter for different features in the picture that it's convolving, depending on how the parameters are set. And we talked about the little knobs being set, and we showed this example. And they don't look, usually the feature maps don't look much like the original photo. In each filter map, or each feature map rather, will filter for different items. And there's usually many of those, hundreds of those in a convolutional neural net. And we talked about, if we had red, green, blue, there would be really 3 times 9 would be 27, and then we usually used a bias function, and the activation function was a ReLU. Okay, and then we also talked about AlexNet and how Alex figured out how he could do a lot of operations in parallel, which really enabled the first use of deep neural nets. And notice the size of this grid here. We've got 1, 2, 3, 4, 5, 6, 7 by 7, and once we convolve it, it turns into a 5 by 5. And that might not be desired. You might want to have it the same resolution on the feature map as you do on the original image there. So you might want the feature map over here to be the same as the original image over there. And also notice that we start to lose resolution around the edges. If you look at the connections to these neuron filters, well, this poor guy in the corner, he only gets one, and she only gets one down here, and then the one really closest to the corner only gets a couple. So you kind of lose resolution. You don't have many parameters looking at those particular blocks. So you lose resolution around the edges, and oh, by the way, the feature map is down. So there's a way to fix this, and it's called padding. And the most common type of padding is zero padding. And what you'll do is pad zeros around the edges. And then when you take the kernel, the convolutional filter kernel, you can kind of let it overlap off the side a little bit. And then these zeros don't really affect it. But yet it gets more looks as it steps across. If you have a strata 1, it steps across, and you can get more resolution that way. And if you do zero padding with one layer on the outside, you can get the same size output feature map as you had coming in. Okay, so that's padding. And one more thing I'd like to talk about is pooling. So that was zero padding, and this is pooling. All right, pooling is a way to downsample. And sometimes we want to downsample. You noticed in that AlexNet how we kept going down in resolution. Well, what wasn't shown there was called a pooling layer. And the way a pooling layer works, the two most common types of pooling layers are a max pooling layer, where it looks for the maximum value within the kernel and it just echoes that maximum value, or an average pooling, where it averages all four, or however big the kernel is, all those values together, and then takes that average and puts it over here. We're showing max pooling here in this example. So this 98 is the biggest number, and it gets pulled over. And if we step this across, if we had a stride of 2, we stepped at 2, then we'd come over here and we'd max pull and we'd take the 34. We'd take another stride, we'd come over there, we'd take the 21. And that's called pooling, and this is max pooling. Okay, so let's walk through a little more of a detailed example. You've got everything you need now to create a modern CNN architecture to identify images. But we'll still keep it somewhat simple, even though this is a bit of a complicated network we're going to design. But we'll keep it a little bit simple. We'll do a 100 times 100 pixel image, and we're going to have black and white, so we'll only have one. We won't have times 3 here. Black and white images of presidents, and we're going to create a neural network to identify presidents. Okay, and you know there's 46 presidents, and that's all you get. That's your problem. Okay, you're going off and you're going to create this thing. But we'll do it together, so no worries. All right, so typically a first layer, we'll use a convolutional filter, and we will use a kernel size of 3 by 3 like we just demonstrated here. We'll use a stride of 1, okay, and then we're going to come up with 32 filters. All right, so we'll have 32 different neurons, and we'll pass those over, making 32 feature maps. And these are the feature maps all stacked together as we pass that kernel over. Remember, this can be done, all of these feature maps can be done in parallel, and all these convolutions can be done with the calculations in parallel. But we can only do one layer at a time, because now we're going to go and we're going to take that layer, and then we're going to do max pooling. We'll use a 2 by 2 square and a stride of 2 like we just did. Now, if I use a 2 by 2 square and a stride of 2, what's that going to do to my resolution? Here I've got resolution the same of 100 times 100, which is what I started for. And once I max pull that, what's this next layer going to be? Yep, you're absolutely right. It's going to be cut in half. So this is going to give you a size of 50 by 50 dimension. So this is going to cut the resolution down by 50 by 50. We're going to crank the filters up. We're going to go from 32 filters to 64 filters. And this is very common, to go down in resolution as you get deeper in your network and to go up in the number of filters. Okay, so we use max pooling to downsample, but then we're going to use a convolution to go ahead and convolve these things. And that filter for that is going to be another 3 by 3 kernel with a strata 1. And then we'll convolve those to make those features map. Then we'll max pull again with another 2 by 2 and a strata 2, take it down in half again. So now we'll get 25 by 25 resolution. But again, we're going to increase the number of filters. We're going to go to 128 filters, from 64 to 128 filters. And you see those stacking up there. All right, then after that, we're going to max pull again, 2 by 2. We're going to take it down yet again to 12 by 12. And now we're pretty much done with the convolution. That should be plenty to do 46 presidents. Might be a little bit overkill, actually. But now we got to flatten that baby out. But that's, basically a vector. That's 18,432 units long. And then that input layer is fully connected to this next layer, right? This next layer of neurons. All right. And then, so that's the 128 layer. So this first layer was just an input layer. That was 18,432. And then this next layer was our hidden layer. That's our 128 neurons. So that's our 128. And then these two layers, the input layer and the hidden layer, are fully connected. So that's a heck of a lot of parameters. And then those are connected to an output layer that's 46 long. And 46 because there's 46 presidents. So each one of those will fire. If we're showing a president here, whichever the more probable president is, that's the neuron that should fire with the highest probability. Now we use an activation function on all these, like we talked about. That's the ReLU activation function, until we get to this last layer. And we use an activation function called softmax. Don't worry about it, but you might, if you hear that, you know what it means now. Softmax just takes and makes this output a probability, because that would, but the whole thing sums to 1 because these are probabilities. So that just gives you a probability so you can see what the network thinks the highest probability is. Okay, so that's the softmax. It just gives you out a probability. So here's kind of, another way to look at that softmax output is a bar chart. And the highest bar, the highest number is going to be the highest probability. So if we ran this through this network in a forward fashion, it's not called a feed-forward network, but it does run through like that. It builds this layer, then it builds that layer, then it builds that layer, then it flattens, then it runs through this. Now, this is a feed-forward network, runs through this feed-forward network, runs through the softmax layer, outputs probability. So let's say it's not trained yet. We run this image through, and it gives us a probability like that. So you can see the highest probability it thinks is the first one, and that's George Washington. Okay, so George Washington's not right. We can see this. That's not right. Matter of fact, I do believe, yep, he's the 16th president. So we're using supervised training here. So the label that goes along with this data point, this supervised learning data point in our data set, is labeled 16. And the way we do this little deep dive, I know, but hang on, it's not that bad. The way we do this labeled data is we connect what's called a one-hot vector to it. And a one-hot vector, so our one-hot vector, that just means 46 numbers, because there's 46 presidents, we'd have a one-hot vector of 46, and only one of those would be 1. Okay, so the label on this would have a one-hot vector with 45 zeros, and that 16th zero from the left would be 16. Okay, so that we compare this output to the one-hot vector, and down here somewhere at 16 would be a 1. So we've got this, and we see almost a 1 here and a whole bunch of little garbage out down here. We use a loss function to subtract the one-hot vector from this to see how bad it was. Okay, so that's where we get our error. And then the backpropagation algorithm takes that error and adjusts all those parameters. And again, you guys don't need these simplified knobs anymore, I don't think. All right, we adjust all those knobs. We backpropagate and we adjust this layer. Then we backpropagate and adjust that layer. And then there's nothing to adjust here. This is just a flattening layer. But then we backpropagate again and we adjust all these filters. So there's 128 filters here. So we adjust, the neurons on all 128 of those different neuron filters. Then we backpropagate again. There's 64 filters here. So we adjust the neurons on all 64 of those filters, backpropagate again, adjust the neurons on all 32 of these filters. And that's one training pass. Okay, it goes forward. It comes out with an answer. We can calculate a loss function from our labeled truth data. We backpropagate, adjust all these parameters, okay? And that keeps going over the whole data set many, 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 many times until it converges, until our error goes to about 0 or converges to some acceptable amount. And then we deem it trained, and then all those parameters stay the same from now on, and we just use it to identify presidents, okay? Piece of cake, easy peasy. All right, so different large language model this time. We'll see if you can recognize the voice. Just came out. Large language model, please summarize this video for me.
Summary of the video. We revisited part 1 and the inception of convolutional operations in AI vision. We then dove into the concepts of zero padding and enhancing our image processing technique. We unpacked the mechanism of pooling, with an example illustrating maximum pooling in action. We then explored a detailed example using a multi-layered precedent identifying CNN architecture. First with a forward pass, a labeled data loss calculation, and finally a backward pass and parameter adjustment.
All right, well, thank you for watching. If you'd like to take any of DAU's AI courses and earn credit toward an official AI training credential, you can click here or look in the comments below for the link. And thank you very much for watching. And if you're getting anything out of these, please like and subscribe and let me know in the comments what else you might like to see. And we do have some Python code for this. Let me know in the comments if you want. We'll drop it in there. Got to admit, just use ChatGPT to pop it out. I'm trying to find a training data set. I haven't actually run it yet. I got to find a data set to do this on. But if I do, I'll let you know how it all works out and make that link available to you.